Okay, so hello everyone. Thank you for coming to listen to this presentation about large language models. And I've tried to vector it towards the interests of let's say with a direction towards computing and so forth, which is not my speciality. But I also have one of my colleagues, Elaine, on board if we get into more practical, experiential questions about how we actually build the models in case they are beyond my horizon of competence. We'll see where we go. So I'm from Silo, which is a largish consultancy company mainly based in Helsinki. We work with many large corporations and many smaller corporations and collaborate with several academic partners and public bodies. We also participate in several EU projects, which is probably the reason we are now having this conversation. We also build large language models. I'll get to that in a bit. Myself, I'm primarily a linguist. I work with language, and these are heady times for a linguist because there's so much fun to be had and so much worry to be worried about because the models don't do quite what we would like them to do as linguists, but they are fun to play with. We'll get to that. I've worked on many things having to do with machine learning in general, on linguistic data, and language models are just one end of it. There are more things to come. So I thought I'd begin by talking about what a language model is. And I'll get to which one of the current language models are large. But language models in general, well, most of you have been exposed to grammars and lexica in school, not least when you try to learn a foreign language, or even to make sense of your own. And strangely enough, most people around me seem to remember that with some level of horror and trepidation. But grammars are one way of describing a language, and in a sense, they're language models. But language models tend to be reserved for such probabilistically or statistically built models that are able to handily compute the probability of a sequence of tokens occurring or the acceptability of it using previous exposure to data. So the idea is that if you have a sequence of tokens, a language model will be able to assess the likelihood of it occurring out in the wild, or provide suggestions for completing or continuing on it and such things. The earliest language models, 50, 60, 70 years old or so, are simple probabilistic calculations. You provide a few words and you ask the model what should come next, or you take a sequence of linguistic items, say words, you blank out something in the middle of it, and then you try to figure out what should be there. Most of us have been exposed to such tests, again, when we're trying to learn a foreign language, try to figure out what should be put in this empty space in this French or German or English sentence, and try to fill it in with something sensible. This is the way our teachers like to, test to see if we picked up any of that French. And this turns out to be a pretty good way of training a general model of linguistic competence. So if you record plenty of what has been said or written previously, it is possible to predict what should happen, what will happen next in a linguistic context. So this is not just a hack. There's an entire linguistic theory about this sort of thing. And this is in contrast with traditional grammars and dictionaries, which would like you to, sit down and properly represent the structure of a language by recording rules and then listing items that can occur and then making sense of the regularities you see. And so the reason most linguists become linguists is because it's fairly obvious when you examine the language, linguistic data, is that it's rule bound to some extent. And some of those rules are a bit fuzzy and flexible, but many are pretty much obligatory. There's very little you can do about word order in English, for instance. but you can do some things, and in some other languages, you can do more, but not anything, and you cannot permute words in any way, and you can't inflect words in any way. And some languages will allow you more freedom in one sense and less in another, and so forth. All of these are fascinating things for those with a little scientific bent, and you end up with a grammar. Those grammars always break, because when you expose them to real usage, you'll find that people don't always behave as expected, and then statistics comes to your aid. So statistical models have proven much more useful, and this is something that I'm not happy about saying publicly, but what has happened in the meanwhile, while linguists were debating how to formulate a linguistic representation, computing came around and built better and better models. Memory is cheap, disks are cheap, processors are effective, and all of a sudden it's possible to make huge statistically trained language models on large amounts of data. This is no thanks to linguistics. This is thanks to computing. Thank you, all computational researchers. This has been what has enabled us to work with distributional semantics. Distributional semantics is the general theory which is represented by a large number of thinkers, both philosophical and linguistic and psychological, which essentially is based on the observation that the meaning of a word can be traced back to a collection of how it's been used. So if you want to understand how a word works, you'll pick up a listing of how it has been used, and that'll help you. This is not the easiest way to learn a language, but if you want to understand a word in the language, not translating it to another language, you can ask, how can I use this word? And you'll get some examples, and that usually helps you figure out what it means. And if someone uses a word at you and you don't quite understand, you might stop and say, hey, I need help here. Please explain what you just said. We don't usually do that. We hold our breath and hope that the word occurs again very soon, and then we can pick up on what it meant. And even a couple of occurrences will usually help us narrow down more or less what it means, sometimes with a little bit of fuzziness around the edges. But this is the way we acquire most of our linguistic knowledge. This is how language models are built. So in practice, just to give you a bit of context why they're around, is that language models have been used for a while to classify linguistic items. You'll have utterances, texts, and collections of documents, and you can use language models to classify them into piles of various usefulness and as a forgiving way of accepting language input. They can also be used to predict what comes next, and using that mechanism to generate language output. And they're built by recording how language has been used. And that has been the bottleneck, it still is the bottleneck. So such language models can then be integrated into systems which help us tell other systems what we want to have done. This has been an interesting, let's say, applicational domain, which has been around for as long as I've worked with computers, since the late 80s at least. My first job indeed was to build a system to accept English queries to a database instead of SQL. It didn't quite work, but it almost worked. And now these things work better and better. During my career in computing, I've many times heard the death knells for SQL. No one will need to write a database query anymore with this new natural language interface. We're getting close to it, but we're still not quite there. But in any case, natural language systems can be useful because they have a forgiving input channel. People say the damnedest things when they mean something quite simple. And if you have a useful natural language system, it'll narrow down what's said it'll map it onto the things you can do with the system. This is why natural language systems are useful at the one end, and language models are a component of them. And you can also have them to build systems which generate language, which will speak language back at you in various ways or produce content. And putting together the recent advantages in language models and language representation, this is how you get, for instance, chatbots, which are of obvious entertainment value and occasionally are useful. They're, above all, they're fascinating to play with. And I suspect most of us, I suspect all of us in this audience have tried out the latest generation of chatbots. And they're, you know, they are fascinating, even for those of us who are prepared for it. And I don't know about all of you, but one of the very first computer labs I had to do in my undergrad degree was to code ELIZA. And I suspect many of you have also done the same. And even ELIZA, with about one page of Lisp code, was fascinating and fun to play with. And today, we're having even more fun. It's a deeply set human, let's say, we have a great readiness to accept and project humanity onto anything that uses language. So even ELIZA, people would argue about, does it actually know what it's saying? I mean, I don't know. That today that seems ridiculous, but those conversations were around then. And today's systems appear to be quite fluent in using language the way people do. We'll get back to this question in a little bit. So, but the general thing here is if you have a language model which has observed a large amount of linguistic data, they can predict what should be there, or they can continue a string. Now, if you see this string there with a blank in it, most people will have no trouble filling in a blank. There are a few alternatives, probably one or two that are more obvious than others. But if you only see the very immediate context, if you just see I, it, you'll have more trouble doing something sensible about it. Now, the English language has, you know, several 100,000 candidate words, and what can be filled in between I and it is a very small subset of those hundreds of thousands or millions of words, but it's still not quite sufficient to do the job. But this is sort of the syntactic constraints we have. There's only some things that fit into that opening in the puzzle. And if you increase it a little bit, you get a much more constrained set of items that can be put in there. So if you get utterances like this and blank out an utterance and test yourself, can I fill it out now? Can I fill it out now? You guess, and then you open the blank and see what's there. And if you do the right thing, you give yourself candy. And otherwise, you know, pinch yourself. And you do this over and over again. This is essentially what language models do. And if you have the full context again, this ought to be fairly easy to fill out. Now, the size of the context window is what determines how well you do in this prediction task. And if you do collect all of these potential constraints based on the surrounding context, you get a pretty large matrix of observations. What could be there? What could be 2 words after bike, or 4, or what is it now? 1, 2, 3, 4, 5, 6 words after hopped, or 3 or 5 words before railway. There's a bunch of words that could be there. And if you tabulate all of these different contexts, you get a large number of parameters. And this is where the large language models comes in. Because if you want to model these things, you get a fairly extensive parameter set that you want to figure out how it works. So how could you represent these data? I mean, one way to do it is to have word-by-word matrices. So what comes right after I in the English language, there'll be a bunch of tokens that could happen just after I. And what comes before it? Well, a pretty large subset of the millions of words or hundreds of thousands of candidate words could come just before it. And if you extend the context a little bit, what can come 5 words before railway? And what can come 5 words before, what was the example sent? What can come before it down to the railway? You get fewer and fewer, but that's a pretty large set of items. And so you might have words by context. So what can come before this, in this context, surrounded by these words before and after. The longer the context, the more reliable the prediction, but the larger the number of contexts. And of course, it's valid to question the whole notion of a context. Say, what is a context anyway? So immediate context, they constrain some aspects, and longer range contexts contain some other aspects. What comes next in this sequence of words I'm producing right now is immediately constrained by the words just preceding it and my plan for the words that will succeed it. And what I started out saying earlier in this conversation also influenced what comes next. And probably on some level, what I say now is influenced by the context that things that happened this morning or what happened back in my school days in the 70s, although it's a bit more difficult to trace that immediate effect. But the larger the context, the better you can model this. And so all of these things govern other aspects of the discourse. And this is a typical lecture situation, so it's probably governed by other lectures I have held and participated in and consumed because the expectations are such that certain things happen, certain things will not happen. One can break them, but that has social costs. Tabulating all of this information is not a practical way to go. So this is why we do nonlinear learning models, so that we won't explicitly have to build these matrices, but have them built by simple mechanisms that are able to tabulate large amounts of data as they go and self-associate the data with itself, essentially doing black box parameter setting. And those of you who worked on wheel statistics, as it were, you know that there's a fair number of hyperparameters, and if you do a black box model, you can dispense with them and hope it organizes itself. This is slightly distressing for those of us who want to do hypothesis-based work, but it turns out it works pretty well. So where are we with language models? They're hugely effective. We can do wonderful things with language models, and you've all seen some of those things, and you can also, you obviously seen some of the more goofy things they can do as well, but they actually produce language surprisingly well. I have to honestly confess, I am blown away by how well they perform. I would not have predicted that even with this parameter size, this size of model, they would do this well. But they're not very efficient. They produce a good job, but at a cost. So I've been given to understand that a human brain runs at about the same effect as a light bulb. And we feed it with cookies and milk, and it runs pretty well. And it's set on top of our heads because it's quite hot. But this is the way it works. And it does quite well. And I was going to add some information about the processing speed of neurons, but it appears that those data have recently been all tossed out, and the neurologists are really arguing about what the processing speed really is. So I won't do a comparison, but neurons are massively interconnected. There's orders of magnitude more wiring in the brain than in a comparable computing device, and that the neurons are, slow on a unit level compared to processor transistors. But still, the effect they consume is quite low. A laptop is much more energy, has a larger energy requirements, and the sort of things I suspect many of you in the audience build are not just one, not just two, a large number of orders of magnitude more, consume more energy or use more energy than the brain does. There's something to be said there because we process language quite handily and learn it as we go. So there's something there that we as engineers need to think about how we might be able to run things more efficiently. More importantly, for the linguist, we know more or less how much language a human is exposed to. A typical human is born without exposure to language. Well, you might have heard some before birth, but it's unlikely you paid much attention. But after birth, depending a little bit on your environment, you're on that order. You're about 100,000 to 1 million words of speech per month, depending a little bit on how verbose your surroundings are. And some kids actually read a little bit as well, but that's marginal compared to the speech you're exposed to. And assuming that you spend your first years pretty much only learning language, and then your adolescent years, you keep learning language, acquiring linguistic competence while you're acquiring other competences as well. You learn to bicycle and pay attention to other people and so forth, sit up straight and do other things. You're exposed to a certain number of words after a while. At about 20 years, assuming that at 20 you've acquired pretty much the competence you ever will acquire in your native language. I mean, you refine it obviously, but at 20 I knew Swedish pretty well. You have 100 million words. You've been exposed to order of 100 million words. I mean, one order of magnitude up or down, but somewhere there. A typical large language model is not trained with that amount of data, not with 10 times that amount of data, not 100, not 1,000, not 10,000, many orders of magnitude more. There's something those of us who are of an engineering bent, should think about there. There's something wasteful going on right there. There's reason to think about, why do we require this amount of energy, and why do we require this amount of data? Also, longer and longer contexts. Getting back to that context thing, I don't know how we might model my current production conditioned on my previous production last night, having dinner, or last week discussing how to fix the bike and so forth. What are those contexts? How do we invoke the right contexts, and how do we select among them? How do we do the training in a more, let's say, precise way? Current models grow in the number of parameters because we use larger and larger contexts, larger and larger data sets, and more compute power to produce them. This is a development trail that would seem not to be sustainable in the long run. But happily, since I pointed out these things about the wastefulness of the energy usage and the data, there's good reason to believe we should be able to make do with much less of both. So let's think about that at some point. There's ample reason to think about it in that way. How might we get more sensible? But this is where high performance computing comes in. I understand many of you work with exactly that. Training a model, it involves setting billions of parameters, many billions, tens of billions of parameters. All of them are floating points typically, using trillions of data tokens in a sequence over a series of training epochs over a data set. Typically, actually only one today, but well, back when we started, we'd run through the training data several times to get it just right. So the procedure is pretty much then. You have this set of training data. You walk through it token by token, word by word, or syllable by syllable, or character by character, depending a little bit on how you set your training system. You walk through it. You try to guess what should be there. You might blank out something that you just saw. You might, be working on the next token. And if you do the right thing, you give yourself candy. And if you do the wrong thing, you pinch yourself. And then you propagate back that. You reset the weights, and then you read the next bit. And you run this through over time. And this takes a fair amount of computation, as you might imagine. Trillions of data tokens, billions of parameters. You start out with a blank slate or a randomly initialized state, and you walk through these data. So many of the hyperparameters, and you can imagine there are many of them, need to be scanned to begin with. That's a non-trivial task, and most of the systems around have pretty much done trial and error there and found settings that work for them. And essentially, the training number of computing steps, it's proportional to the number of parameters and the number of tokens in the training data. That's, steep when you factor it out. And the training memory need is proportional to the context length you're working with squared, because what you're doing is you're looking at all the words at the same time, trying to figure out which of those influence what you're looking at. There are ways of getting around this, but this is sort of the maximalist view of what needs you have. Now, this is what the engineering thing then boils down to some of these these training procedures are quite lengthy. They're not momentary blips, and they're not easily hacked up in chunks that can be done when some processing cycle frees up, because these models are large. So the overhead for reading one into memory or sharding it and getting it ready to be trained is huge. And then if you're in your allotment of computation time, writing it back onto disk or whatever way you do it is also expensive. So the training procedures for these sorts of runs are very different from some other types of high performance computation efforts. This has caused some friction, I know, between people who build models and people who provide computing resources, because the computing resources are shared out in a way which is suitable for some types of, say, aerodynamics tasks, but those tasks are very different from these types of tasks. So, and this is something we need to think about, because the needs are different from training this type of very data-rich foundation models. Foundation model is the word of the day. This means you train a huge model. You don't train a specific model for a task. You train a huge model, and then you tune it for different tasks. So you have a base model, a foundation model, and that is supposed to encompass a language, if you will, and then maybe several languages plus general linguistic capability of people. And then you tune it for a task using further refinement runs, which are then less expensive, is the general sense. Now, base models are rapidly becoming a commodity. There are many being built, and they're all different in various ways. There's no consensus about what the best type of model would be yet, but they share architectural characteristics to a large extent. And there's a general push to build large European-based models that can run with many languages simultaneously. Instead of having one per language, the idea is you have cross-linguistic effects, which are very true. If you train a language model on several languages, you'll find you need less data for the nth language than you needed for the first one. There's some contamination there. There's some mess-ups happening. But in general, the similarities between human languages are larger than the differences between them. So you actually do win from training a model in several languages if you do it right. And you want these to be able to be applied to tasks by various downstream stakeholders, public bodies, even small enterprises and large enterprises, if you will. The Commission is funding such projects, and Silo participates in a couple of them. And the idea is we want to have models that fit the European scene in various ways. And there's, of course, an interesting challenge into figuring out, are these models indeed carriers of European values, and do they contribute to digital sovereignty of Europe? Are they strategically autonomous models? How can we measure these things? Are the quality standards we use different from those used in California, say? I mean, some sense, obviously yes, and in some senses, obviously no, since they're all human. Once you have one of those, foundation models, and reminding you again, huge computational requirements, it must run somewhere. Deploying a train and tune model needs a host for running what's called inference jobs. And the current business models are based on paper token. So what you do is you have a bunch of stuff you want to do with the model, and you want the model to produce some stuff or converse with you in some way. So you want to run, you want to calculate how much you utilize the model. This is probably not the last word on the business models, but currently they run somewhere. Now, the computation cost there is pretty much, it's proportional to the length of the input in tokens or words and in the number of parameters of the model. And to some extent, the length of the output as well. This has led to and the memory needs is proportional to the number of parameters you have in your model. These are, as you understand from the previous conversation, these are large numbers. The input links and the output links, they're handy, but the parameters are still in the billions. In effect, the serving a model is much cheaper than training a model, but it's still huge. It's not something that'll run on a wristwatch anytime soon. But the ambition is to get there. Also, the workload and the demand for these models may be much larger than the training model. Essentially has the one user training the model. But if you field a neat model that does interesting things, you might expect many people to want to run it 24/7. The service level agreement is different from training jobs. And all of these things, I mean, they interact into building a very engineering-wise complex world. So what we do when we train models, we save them as we go. So we have checkpoints that have partially been trained with a smaller parameter size. We quantize to turn the essentially continuous floating point parameters to integers and to small sets of integers. And that is an ongoing research to see how that best might be done. Models in general are over-parameterized. The number of parameters is giganormous, and we don't quite need that entire space. So can we distill them into something more sensible? This is ongoing work again. The challenge here is that the models we emulate, namely the human models, they learn as they go. And if we have a too complex compilation step of downloading entire libraries of human knowledge, training a model over several weeks or months of HPC time, fielding it, tuning it, and then distilling it, we're a long way from the online learning we would like to see. We have low-ranked specialization models. We have the idea being that we have a foundation model, which is hugely over-parameterized, and then we build using various manipulation techniques, linear algebra, we build a low-dimensional model, low-ranked model, as it were, to capture certain characteristics that we want there to be persistently. And those models can then be used for, say, if you have a general foundation model, you could build a low-ranked model to capture the characteristics of a certain genre, even a certain author, or a certain type of situation. And those can be trained way less expensively than previous ones. This is essentially a hack, because this is not the way we should be going. This is me glaring at my colleagues, but many people disagree with me there. We'll see. At Silo, we're building a model which we're quite proud of. We're building it together with Turku. Turku University is one of the larger ones in Finland. The current release we have handles Finnish and English and the computer code quite handily. It's probably the best Finnish language model around. It has decent, if not state-of-the-art, capacity in English and code. It's trained on Lumi with about 1 trillion tokens, which, as I indicated previously, is a serious amount of data. It's entirely open, more open than many other models around, and it does really well. It also surprisingly knows some other languages. Testing it in Swedish and Spanish actually provides some output. That's typically quite right, because everything is a bit multilingual. This is our first series of models, and we will be releasing another model soon. I think the first checkpoints are out, and my colleague Elaine might be able to give more detail if you're interested, of a Nordic model. I know we've released a first checkpoint. We might not have instruct trained it properly yet, but it's coming along quite nicely for the Nordic languages and Finnish and English and code. And we're training a larger one later this year for most European languages. Now, Lumi is a very special setup. Many of you probably know more about Lumi than I do. It builds itself at the most powerful supercomputer in Europe, which probably is more or less true. It has huge performance. It runs on green energy, which is nice. It's built on AMDs, which makes it unusual. And we use a certain standard stuff to train our model. Now, Lumi is very special, which makes it challenging to run huge efforts on this. I've heard numerous expressions of frustration from my colleagues doing the actual training, because AMD architectures are slightly different than the standard, more standard NVIDIA ones. But there's a certain point to doing stuff. And on different architectures, you get a bit more resilience from testing things on several architectures. There's a bunch of learning we've done going along the line, training on Lumi. And we're quite happy to share much of this as we go forward, training more models. So this is all about where we were and where we are. And the question is next, where do we want to go? And so some of these questions, some of these ideas might be, I'm trying to stay realistic here, but there are some things that, of course, are a bit difficult to predict. Now, we do know that the data requirements are, well, I've written enormous here in the slide I see. I should say they're enormously wasteful. We shouldn't need that much data. Can we lose the L in the large language model? Can we do just language models, please? We want better learning curves. We want to be able to learn from a smaller amount of data. And how might we be able to do that? Well, we could be, again, as we were at the beginning of the language model general project, be inspired by the way humans do it, by thinking about the way we learn language is mostly by observing and not by teaching. And the way we learn language is by observing it in context. It's being used for something. There's intentionality in language use. There's plenty of contextual variables. When people tell us, watch out, that's dangerous, there's usually a bit of emphasis and something dangerous around to anchor it. And this is a richer signal through more contextual data and through more anchoring. And this means that to do this well, we should move from pure text to a more multimodal setting. And we should probably move from learning by observing to the occasional teaching episode. These are two different things, I should stress here. We want to have richer data and we want to have more focused observation of those data. Now, frequently we hear things about, are we moving towards artificial general intelligence? Are we moving are we not just building a language model? Are we building a general intelligence? Certainly, this is the ELIZA factor that I mentioned at the beginning. It's easy enough to ascribe intelligence to something that responds intelligently. And language models are able to reason using language because they've memorized much of how one reasons. And this is the way we learn things as people. I mean, Aristotelian syllogisms are built that way. We just learn to figure out certain things, and then we use those patterns and templates for future situations. But this is not the only way we learn things. And we certainly don't learn arithmetic by memorizing stuff. We did memorize the multiplication tables, but that didn't mean we understood multiplication. I mean, all of us in this room probably have memorized multiplication tables because that's what we had to do in grade school. But really knowing how multiplication goes down means actually understanding them in a different way. So language models are able to reason and compute, but sometimes they make really stupid errors doing so. And the reason they make stupid errors is probably because memorizing patterns is not really what they should be doing on that level. That means they're leaving the realm of being language models. So we should think about the second L. I suggested a little bit we might want to lose the first L for the future generations of language models. And we should think about, what do we want a language model to do? What is the scope of a language model? Is it supposed to be a general purpose reasoning capable machinery? Or when we do reasoning, should we maybe make a call to a reasoning agent that does the reasoning for us, and we use the language model for expressing and understanding what's going on in ways which allow us to do the right calls to those reasoning agents. And this is an ongoing conversation within the language modeling community. And we have wildly varying positions in this general question. Another related question is, of course, that language models, if they're trained on data, they're liable to use that data to say things, and some of those data may be obsolete, annoying, offensive, or even criminal. And some of us would say that we need to constrain the language model so that they don't do bad things. And some of us, again, would say that the language model should be allowed to, say whatever it can, and we should have another way of constraining a system not to do the damnedest things, because all of us are able to say the wildest and most offensive or surprising or disjoint utterances at any time. We just choose not to because of something else. It's not our grammar constraining us from doing that, but it's there are other aspects in play that govern our behavior. And maybe we should think about what is the scope, again, what is the scope of a language model? Should it be generally competent in every aspect of language? And should there be other modules governing it? Or should we expand it so that we don't have a large language model, that we're actually doing a large reasoning model or a large behavioral model, and then the jury's out with how to govern that. These are questions that will then have effects on how we train and how we compute using them. So they will have effects on how we build training and how we build serving computation. And I guess that's pretty much what I wanted to convey to you guys. So firstly, language models are huge. And as you may have understood from what I said, I am of the opinion they're too large because of engineering concerns. Training them, it does involve very specific computing requirements and computational infrastructure. And we're happy to see that being provided to us by good people who build huge machinery. And as you may have understood, I am of the opinion we should be able to make do with less. Serving them also involves a huge computational effort. And we do know that in the future, we will expect to have models running on wristwatches and mobile devices as well. So serving models on the edge is an important thing for future application. How we will achieve that is an interesting engineering effort. It is quite likely that the models will evolve from just using pure text to use a richer signal. And this will hopefully lead to smaller models because we will have a richer signal, a denser representation, and we may need less parameters to model them in. This is a slightly contentious position, but I'm not alone in claiming this. This will not lessen the demands for training, though, but hopefully it will lessen the demands for serving. Now, model architecture, the models of today are there are families of models that argue among themselves about how things should be built. They will change as we go along. We're not at the end of history here. They will change dramatically, quite likely, within the next years, even months, because things happen quite rapidly now. And so many of the things I said, many of those back of the envelope calculations about requirements I made might change very rapidly. But it's very clear that runtime demands are likely to increase and reliability requirements with them. People will want these models to run reliably all along. Yes, that was pretty much what I intended to say. And I think I'm pretty much on time. I don't see the time on my screen right here, but I think we could move to questions at this point.
Yes.